In the 20th century, rockets carried humans beyond Earth for the very first time. We touched the moon. We sent probes to every planet in the solar system. Suddenly, the idea of living on other worlds no longer seemed to belong only to our imagination. It felt like a future waiting to happen. But decades later, the dream has stalled. We have not returned to the moon in half a century, and Mars remains as distant as ever. Every serious plan for a permanent human presence in space runs into problems that seem less like temporary setbacks and more like fundamental walls. What if humanity will never leave Earth for good? What if the idea of becoming a spacefaring species is not our destiny, but a fantasy? Why we mistake rocketry for simple freedom. When people think of rockets, the image that comes to mind is one of freedom. A sleek machine rising into the sky, flames pouring out beneath it, carrying humans away from the ground and into a new world. The countdown begins, the engines ignite, and suddenly the craft tears itself free from the planet. In just a few seconds, the ship seems to slip from Earth's grasp. For many, this image creates the belief that rockets are simple tools for liberation, a fast ticket to anywhere beyond the sky. Yet the truth is far from simple. Rockets are not symbols of casual escape. They are machines that fight against the strongest force we know in our daily lives, Earth's gravity. And they do so at a cost that people rarely acknowledge. From early science fiction novels to modern blockbusters, rockets have been painted as near-magical vehicles. A hero needs to leave Earth. The ship is waiting on the launch pad, and within a few minutes, it breaks into orbit. These portrayals compress months or even years of planning into a single moment of dramatic ascent. The engines roar, the camera shakes, and before long the characters are weightless. There is rarely mention of the staggering quantities of fuel required, the detailed calculations of trajectory, or the hair-thin margin of error between success and catastrophe. Movies and shows smooth away the difficulties, leaving the impression that flight beyond Earth is no more complex than catching a long-distance train. Human beings are used to planes. We board them, sit in a chair, and within hours, find ourselves on the other side of the planet. The leap from plane to rocket feels, in cultural imagination, like an extension of the same idea. If a plane can cross oceans, surely a rocket can cross space. But the two are not the same. A plane moves through air, lifted by wings and powered by engines that sip oxygen directly from the atmosphere. A rocket must carry all of its own oxygen and fuel, burning it at an incredible rate just to rise above the pull of the planet. To reach orbit, a spacecraft must travel at more than 28,000 kilometers per hour. This speed is not a luxury but a requirement. Anything slower and the craft will fall back, crashing to the Earth it tried to leave. The cost of achieving this speed is almost unimaginable. A modern rocket, like those used to send satellites or astronauts into space, carries hundreds of tons of propellant. Most of the structure we see on the launch pad is not the spacecraft at all, but the fuel needed to push it upward. The actual capsule or satellite, the thing that survives the journey and continues into orbit, makes up only a tiny fraction of the total mass. In fact, around 90% or more of a rocket's weight at launch is fuel. The vehicle sacrifices itself in stages, dropping empty tanks to shed weight, just so that a small piece of it can continue the journey. What looks like freedom is actually an enormous, carefully timed act of destruction, where much of the rocket is left behind in the attempt to escape gravity's hold. During the space race of the 1960s, rockets became icons of possibility. They represented progress, power, and even hope. Images of Apollo launches made their way into homes around the world, showing flames, thunder, and triumph. What was rarely shown was the years of failure that came before. The destroyed prototypes, the astronauts lost in training accidents, and the countless calculations that had to be done before a single launch was even attempted. The public was fed the highlights, the heroic successes, which cemented the idea that rockets were clean paths to the stars. The messy reality, full of trial and error, remained in the background. The simplification continues in modern times. Private companies broadcast their launches with sleek visuals and celebratory language. They promise futures where rockets may one day carry people between cities or even to Mars, as though it is only a matter of waiting for the tickets to go on sale. The true challenges, engineering reliability, human safety, resource costs, are often left in the fine print. This is not deception so much as it is marketing. Spectacle sells, and nothing captures attention like the sight of a rocket cutting upward against the sky. The danger is that this repetition of simplified images builds a cultural memory, where rockets equal easy departure, where leaving Earth is no more complicated than leaving a driveway. But to leave Earth is to push against one of the most stubborn barriers in nature. Gravity binds everything to the planet. It holds oceans in place, keeps the air around us, and shapes the very path of the moon. To escape its pull requires not just power, but precision. A rocket cannot simply go straight up and keep climbing. If it did, it would eventually run out of fuel and fall back down. Instead, it must arc sideways, gradually building up speed until it is moving so fast that Earth's curve drops away beneath it. This motion is more like falling around the planet than leaving it. To maintain orbit, the rocket must reach the perfect balance of height and speed. Every launch is the product of thousands of people, years of effort, and billions of dollars. What looks like liberation from Earth is, in fact, the most constrained and difficult kind of travel we have ever attempted. Popular culture erases this struggle, because stories are easier to tell when the machines simply work, when the heroes reach space without confronting the full weight of what it takes to get there. Yet behind every smooth image of ascent is a hidden mountain of effort. We want to believe that the sky is open, that we are only a few steps away from leaving behind all the problems of Earth. Rockets embody that dream in shape and motion, rising on fire and thunder, as if tearing the chains of gravity apart. But to mistake that symbol for reality is to overlook the challenge that still defines our age. Why returning to the moon was harder than it looked. When the Apollo astronauts first set foot on the moon, it seemed as though humanity had crossed a permanent threshold. Images of astronauts moving slowly across the grey surface, planting flags, collecting rocks, and looking back toward Earth gave the impression that the moon was only the beginning. The way it was broadcast around the world suggested that space travel had entered a new era, one where visits to the moon would become as regular as flights across the Atlantic. The sight of a spacecraft leaving Earth, traveling 250,000 miles through space, landing on another world, and returning safely, created the illusion of routine. Yet beneath that illusion was a fragile, costly, and deeply complex effort that pushed technology, money, and human endurance to their limits. The Apollo missions were extraordinary achievements, but they were never sustainable in the way they appeared. One reason for this gap between appearance and reality was cost. Apollo was, at its peak, one of the most expensive projects ever undertaken by the United States. The program consumed billions of dollars in the 1960s, at a time when those amounts were even more staggering than they sound today. Entire industries were mobilized to build the rockets, spacecraft, computers, and suits that would make the missions possible. Hundreds of thousands of people worked directly or indirectly on Apollo. The rockets themselves were enormous, with the Saturn V still standing as one of the most powerful machines ever built. Each launch was not just an engineering feat, but an economic one, demanding resources that could not be easily justified outside of the political urgency of the Cold War. That urgency was another factor often overlooked when people wonder why humanity did not simply return to the moon. The race to land there was not driven only by science or exploration. It was fueled by competition with the Soviet Union. The moon became a stage on which two rival nations demonstrated power, technology, and ambition. Once the United States succeeded in landing astronauts and returning them home safely, the symbolic goal was achieved. The world had seen American astronauts walking on another world, and in the eyes of leaders at the time, that victory was enough. Without the same level of political pressure, the enormous costs and risks of continuing regular missions lost their justification. Even during the Apollo program itself, the risks were constant. The missions were carefully planned and executed, but they were also fragile. A spacecraft traveling to the Moon and back was not robust in the way we often imagine. The lunar module that carried astronauts down to the surface was thin, lightweight, and delicate. It was designed only to work in the vacuum of space and under the low gravity of the Moon. Its walls were so thin that astronauts compared them to heavy-duty foil. If anything had gone seriously wrong, there was no backup. Apollo 13 famously showed just how close disaster could come. An explosion in the spacecraft forced the crew and mission control to improvise solutions to bring the astronauts home alive. That mission ended without a landing, but it revealed how narrow the margin of safety truly was. The complexity of these missions added to the difficulty of repeating them. Launching from Earth was only the first step. The spacecraft had to separate, reconfigure, and fire engines at precise moments to escape Earth orbit and aim for the Moon. Once there, part of the spacecraft had to break away and descend while another part remained in orbit. After the surface mission, the two had to reunite in lunar orbit, dock together, and then fire engines again to return to Earth. Finally, only a small command module survived re-entry through the atmosphere, plunging back at tremendous speeds and surviving by means of a heat shield. Every stage involved delicate timing, exact calculations, and equipment that could not fail. When people today look back, it can seem as though landing on the Moon was straightforward. But in truth, each mission was a long chain of fragile steps, each of which could end in disaster if anything went wrong. After Apollo ended, the expectation among many was that humanity would keep going. Some thought that permanent lunar bases would be built, while others dreamed of Mars missions following soon after. Instead, the opposite happened. The Apollo program wound down, and there was little appetite to spend at the same level again. The Vietnam War was draining American resources. Social programs and other domestic priorities competed for funding. Politicians saw little reason to continue pouring billions into missions that no longer carried the same symbolic weight. By the mid-1970s, the Apollo era was over, and there were no concrete plans to return to the Moon. In the decades that followed, space exploration did not end, but its focus shifted. The Space Shuttle was developed, offering reusable vehicles that could carry astronauts into low Earth orbit. Instead of traveling outward, missions focused on building infrastructure closer to home. Satellites, space stations, and telescopes became the main tools of exploration. While these projects advanced science in many ways, they reinforced the idea that venturing back to the Moon was not a priority. The shuttle program itself, though ambitious, consumed large amounts of funding and required constant maintenance. The International Space Station absorbed even more resources. With so much invested in near-Earth operations, there was little room left for lunar expeditions. Technological challenges also made a return harder than it seemed. Although Apollo had succeeded, it did not leave behind a robust, ready-to-use system for future missions. The Saturn V rockets were retired, and the production lines that built them were dismantled. The specialized skills and knowledge faded as workers moved on and the years passed. Rebuilding that capability from scratch would require a massive investment of money and time. The idea that humanity could simply dust off the plans and return to the Moon ignored how quickly aerospace technology changes and how difficult it is to recreate the infrastructure of the 1960s and 70s decades later. Another factor was the human perception of danger. Apollo astronauts were willing to face enormous risks. The missions were dangerous and those involved knew it. But as time passed, public tolerance for risk in spaceflight decreased. Each tragedy, such as the Challenger and Columbia shuttle disasters, reminded the world of the human cost when things went wrong. These events made governments and agencies more cautious. The Moon, with its distance and difficulty, seemed too dangerous for missions that did not have a clear purpose beyond prestige. Exploration gave way to caution, and caution slowed progress. The question of why we have not simply gone back often assumes that technology naturally advances in a straight line. In many fields, progress is steady and builds upon itself. But space exploration does not work in the same way. It depends heavily on funding, politics, and priorities. The Apollo missions were not the start of an inevitable march outward. They were a peak made possible by unique circumstances, a mix of competition, ambition, and national pride. Once those circumstances faded, the peak was followed by a decline. Returning to the moon required more than just desire. It required rebuilding the massive framework that Apollo had relied upon, and without strong reasons to do so. That framework never materialized again. In recent years, talk of returning has resurfaced, fueled by new technology and new players. Private companies promise lower costs and innovative designs, while nations see the moon once again as a strategic and symbolic goal. Yet the long gap since Apollo shows just how hard it truly was. The dream of a simple return was always an illusion, built on memories of televised triumphs rather than the reality of fragile machines and extraordinary costs. The moon has always been within sight, but reaching it is a reminder that what looks routine in history books or documentaries was, in fact, one of the hardest things humanity has ever done. The rocket equation's paywall. The rocket equation was worked out in the early 20th century by Konstantin Tsiolkovsky, one of the pioneers of spaceflight theory. At its heart, the equation simply describes how the velocity of a rocket depends on how fast its exhaust gases are pushed out, and on how much of the rocket's starting mass is fuel. On paper, it looks like a clean formula. In practice, it dictates everything about what rockets can and cannot do. It reveals that rockets can only reach higher speeds by throwing away a huge percentage of their own starting mass. The more speed you need, the larger that sacrificed fraction becomes. For missions that require escaping Earth's gravity, that percentage becomes enormous. This is why rockets look the way they do. The consequences of this equation are punishing. Suppose you want to send a heavier object into space, like a larger satellite or even a spacecraft capable of carrying supplies for long journeys. The instinct might be to simply build a bigger rocket, but the rocket equation resists this idea. As the payload gets heavier, the rocket must carry more fuel to push it. That added fuel itself adds weight, which demands still more fuel. This loop quickly spirals out of control. A rocket large enough to send truly heavy loads into deep space would need to carry so much fuel that it becomes almost absurdly big. Even if you could build it, the cost and engineering challenges would be staggering. This is why most of the rockets we see launched today look similar in scale, despite advances in technology. They are all fighting the same mathematical barrier. To push against Earth's gravity well, they must devote nearly all of their structure to fuel. The payload remains tiny compared to the whole. In some cases, only a few % of the launch mass makes it into orbit. The rest is fuel burned away or discarded tanks falling back into the ocean. This imbalance is baked into the physics of how rockets work. One way engineers have tried to deal with this problem is through staging. A single rocket carrying all of its fuel in one piece would be so heavy that it could never escape the cycle of adding more and more propellant. By splitting the rocket into stages, engineers can drop empty fuel tanks and engines as they are used up. This reduces weight step by step, making it possible for the remaining stages to accelerate further. Staging does not break the rocket equation, but it works with it, allowing us to squeeze more performance out of the same math. Without staging, the moon landings would never have been possible. The Saturn V rocket, for all its power, could not have carried its payload to the moon in one piece. It succeeded only because it shed parts of itself along the way, like a tree shedding branches to let the core climb higher. Yet even staging has limits. If you want to send something much farther than the moon, say a crewed mission to Mars, you face the same wall. The spacecraft will need not just enough fuel to leave Earth, but also fuel to slow down when it arrives, and then more fuel to leave Mars and come back. Every drop of that fuel has to be carried from the start, stacked on top of itself, magnifying the weight and feeding the cycle once more. In theory, you could keep adding stages, but in practice, this becomes unwieldy. A rocket tall enough to hold all that propellant would be too large to build or launch. The costs would skyrocket long before the rocket itself did. This is where the dream of building ever bigger rockets runs into reality. People often imagine a future where we simply build machines large enough to carry whole colonies of people and supplies across the solar system. Science fiction fills the mind with images of giant ships rising from the ground, as though scaling up is just a matter of building bigger factories. But the rocket equation shows why that dream does not translate easily into practice. The growth is not linear, it is exponential. Each step upward requires far more than the step before. The difference between sending a small satellite and sending a heavily loaded spacecraft is huge within the current framework of rocketry. Some have tried to get around this by proposing new methods of propulsion. Nuclear thermal rockets, for example, could heat propellant with reactors instead of burning chemical fuel, giving a higher exhaust velocity and thus a better performance under the rocket equation. Other ideas, like ion drives, solar sails or fusion propulsion, imagine ways to push against the equation's limits by offering much higher efficiency. But these remain either experimental or theoretical. For now, the rockets we launch rely on chemical propellants, and chemical rockets remain tied to the harsh trade-offs of Tsiolkovsky's math. Satellites, space stations, and telescopes in orbit are all within the reach of current rockets, even if they require careful planning and heavy funding. Missions that go farther, like probes to Mars or beyond, are far rarer because each one stretches the limits of how much payload can actually be delivered. And when we talk about sending humans instead of machines, the difficulty multiplies. Life support, shielding, food and return capacity all add weight. Each kilogram of added mass demands more fuel, and the loop begins again. This reality has shaped not just the technology of rockets, but the very pace of exploration. It explains why, decades after the moon landings, we still have not sent humans farther. The barrier is not simply money or politics, though those play major roles. The deeper issue is that rockets are bound by a law that makes scaling up extremely punishing. It is not that engineers lack imagination. It is that imagination itself collides with physics, and the rocket equation always has the last word. For the dreamers, this equation feels like a chain. It sets limits on what we can attempt with the tools we have. For those who design rockets, it is a constant challenge that forces every choice to be made with efficiency in mind. The fuel tanks, the engines, the stages, all are dictated by the unforgiving balance of mass and velocity. It is why a rocket on the launch pad looks impossibly large, but carries only a small capsule at its tip. The sheer scale hides the truth that almost everything you see is fuel, and almost nothing that matters survives to orbit. The rocket equation does not forbid us from leaving Earth, but it charges a price so steep that only the most carefully planned missions can pay it. Every dream of going farther, whether to Mars, to asteroids, or to distant stars, runs into this paywall. Until we find ways around it, whether through new propulsion or entirely different concepts of travel, rockets will remain machines that give us only limited freedom. Chemical rockets and their limits. Chemical rockets are an odd choice for something as ambitious as space exploration. The principle behind them is simple. Fuel and oxidizer are mixed and ignited, creating a violent release of energy. The exhaust gases are forced out of a nozzle at high speed, pushing the rocket in the opposite direction. It is a straightforward application of Newton's third law. Every action has an equal and opposite reaction. For centuries, this idea was only seen in fireworks and early rocketry experiments. It was never meant for carrying humans to other worlds. Yet today, after decades of advances in technology, we still rely on the same method. Chemical propulsion has carried every astronaut into space, every satellite into orbit, and every probe on its first steps away from Earth. At the same time, chemical propulsion has locked us into a narrow cage of possibilities. It is powerful, but only just enough. It works, but only at extraordinary cost. It is both the foundation of spaceflight and its greatest limitation. The engines of a launch vehicle like the Saturn V or the SpaceX Falcon 9 generate millions of pounds of thrust. This is necessary to lift a spacecraft out of Earth's gravity well, which is one of the hardest tasks in spaceflight. No other propulsion system we currently have can provide that kind of immediate force. Nuclear engines, ion drives, or solar sails may offer higher efficiency in theory, but they cannot yet produce the sheer power needed to overcome the first step, getting off the ground. For this reason, chemical rockets remain essential. They are the only known tools capable of bridging the gap between Earth's surface and orbit. But once that gap is crossed, their weaknesses become clear. Chemical rockets burn through fuel at astonishing rates. During a launch, a rocket can consume thousands of liters of propellant every second. This fuel does not scale efficiently. If a mission requires carrying more mass, the rocket equation ensures that fuel requirements balloon far beyond what is practical. The efficiency is brutally low. This trade-off becomes even harsher when missions extend beyond Earth orbit. Each added maneuver requires more fuel. The problem is compounded when human missions are considered. Machines can be made small and efficient, stripped down to their bare essentials. Humans need food, water, air, shielding, and room to live. All of these add mass, which adds fuel requirements, which adds more mass. Another issue is that chemical rockets carry everything they need from the start. The fuel and oxidizer must be stored inside the vehicle, loaded and ready before launch. There is no refueling once the engines ignite. Once the tanks are empty, the rocket is finished. This limits both range and flexibility. A chemical rocket can only perform the mission it was designed for. If conditions change, if the spacecraft needs to adjust course dramatically, or if it needs to travel farther than planned, there is little margin to do so. The propellant is a fixed budget, and once it is gone, the mission is over. The limits of chemical propulsion are why most of the farthest-reaching spacecraft we have built are small robotic probes. Voyagers 1 and 2, for instance, launched in the 1970s and are now the most distant human-made objects in space. They did not get there by carrying enough fuel to travel billions of kilometers. Instead, they used clever trajectories, stealing energy from planetary flybys to gain speed. Without those gravity assists, chemical propulsion alone would not have been enough to carry them so far. The probes themselves are tiny compared to crewed spacecraft, and even then, their journeys relied heavily on external help. This highlights the sharp line chemical rockets draw. They can deliver small, carefully designed machines across space, but not massive cargo or large crews. Despite these shortcomings, we continue to use chemical rockets because no other method has reached the same level of reliability. Ion engines, for example, can run for months or years with high efficiency, but they produce only a gentle push, far too weak to lift a rocket off Earth. Nuclear propulsion could, in theory, provide greater efficiency, but it carries enormous safety and political challenges. Solar sails require vast, delicate structures that must be deployed in space. Until these alternatives mature, chemical rockets remain the only practical solution for getting into orbit and beyond. Carrying enough supplies for a Mars colony, along with equipment for survival and return trips, quickly becomes an impossible task with chemical fuel. Even if such a mission were attempted, the number of launches required to assemble all the needed mass in orbit would be staggering. Each launch would cost hundreds of millions of dollars, and each would depend on careful timing and success. The dream collides with the limits of the fuel. The situation becomes even more daunting when considering journeys beyond Mars. To reach Jupiter, Saturn, or farther, spacecraft must travel for years or decades. Carrying enough chemical fuel for such trips is not feasible. Probes can manage because they are small, use minimal power, and can rely on careful trajectories. But for human missions, with their enormous requirements, chemical propulsion simply cannot provide enough. It is striking, then, that our entire spacefaring age is built on this method. From the first launches in the 20th century to the most advanced rockets today, the principle has not changed. The engines have become more reliable, the fuels more efficient, the design's more sophisticated, but the underlying method remains the same as that used in the first experimental rockets. In other fields, technology tends to evolve rapidly. Computers grow smaller and more powerful. Energy sources diversify. But in rocketry, chemical propulsion has remained the default for decades. It shows how far a single method can take us, but it also shows the limits of pushing one tool beyond its natural boundaries. The hidden mass of support: launch pads, fuels, and supply chains. Behind every launch is an invisible web of infrastructure, supply chains, and support systems that never leave the ground, but are as essential to flight as the engines themselves. Without this earthbound backbone, no spacecraft could rise beyond the atmosphere. The launch vehicle is just the visible actor. The stage on which it performs is vast, heavy, and unbelievably expensive. Take the launch pad, for example. From a distance, it looks like a concrete slab, perhaps with a tower beside it. In reality, it is a colossal piece of engineering. A launch pad is built not only to hold the rocket, but to withstand the violent forces unleashed at ignition. Exhaust gases from chemical rockets can reach thousands of degrees, and the pressure wave alone is enough to shatter concrete if unprotected. That is why flame trenches, water deluge systems, and sound suppression technologies are built into modern pads. Billions of liters of water may be dumped in a matter of seconds during a launch, just to absorb heat and dampen sound waves that could otherwise bounce back and damage the rocket. None of this is reusable. Pipes must be replaced, valves maintained, and concrete repaired after each flight. Every launch leaves scars on the ground infrastructure, demanding crews of workers and constant investment to keep the site functional. Beyond the pad itself, there are the towers. These are not just scaffolding, but elaborate service structures filled with access arms, fueling lines, and safety equipment. They allow technicians to reach the rocket's payload bay, fill cryogenic tanks, and keep the vehicle stable in the face of winds. The cost of building such a tower runs into hundreds of millions, and they cannot be easily relocated. Each pad is a permanent monument tied to geography, climate, and political circumstance. When nations talk about building new launch sites, they are not speaking of weeks or months, but years of construction and billions of dollars invested in infrastructure that may only serve a handful of rockets each year. The fuels themselves form another hidden burden. Chemical rockets often rely on cryogenic propellants like liquid hydrogen and liquid oxygen, which must be produced, transported, and stored under extreme conditions. Liquid hydrogen boils away at just a few degrees above absolute zero, demanding tanks lined with advanced insulation. Even then, losses are inevitable. Simply keeping the fuel in storage without it evaporating requires a constant fight against physics. The production of these fuels is energy intensive, involving large industrial plants that run continuously to keep pace with launch demands. Each tank of propellant represents not only the chemical energy stored inside, but also the massive energy footprint that went into making it usable in the first place. Moving that fuel from plant to pad is a logistical challenge. Specialized trucks, pipelines, and storage spheres are needed, each with strict safety requirements. A single accident in the chain can set back launches by weeks or months, since the volatile nature of rocket fuels means contamination or mishandling is catastrophic. At the pad, the fueling process takes hours, requiring teams of highly trained technicians in protective suits watching carefully for leaks. One small leak of hydrogen, which is invisible and nearly undetectable without sensors, could lead to an explosion capable of destroying not just the rocket, but the entire launch facility. Thus, fueling is not just an engineering task, but a dance of precision, safety, and enormous cost. Yet fuel and pads are only the surface of the hidden mass. Behind them stretches a supply chain that extends across the globe. A single rocket may contain millions of parts sourced from dozens of countries. Metals must be mined, refined, and machined into precise components. Electronics are fabricated in cleanrooms that themselves cost hundreds of millions to operate. Every bolt, cable, and circuit is tracked, tested, and certified. The assembly of a rocket is not a simple act of construction. It is the coordination of industries on a national or even international scale. Just as an airliner requires airports, control towers, and maintenance crews, a rocket requires a world of infrastructure, but on an even grander scale, because the tolerances are far less forgiving. Thousands of people are employed not only at launch sites, but in factories, research centers, and transport companies that support spaceflight. Their work is largely invisible to the public eye. Engineers ensure cryogenic lines don't rupture, welders piece together tanks that can withstand immense pressure, and logistics teams coordinate deliveries down to the hour. These workers may never see the rocket they helped launch, but without them, it would never exist. One reason why launches remain rare, even in the 21st century, is precisely because of this invisible burden. Unlike airplanes, which can take off and land from thousands of airports worldwide, rockets are chained to a few carefully designed pads. Each launch requires months of preparation and the coordination of vast supply lines. If a rocket fails, the setback is not just the loss of hardware, but the disruption of an entire industrial rhythm. Recovery takes time, and time costs money. This is why nations guard their launch facilities so carefully, and why private companies, despite pushing for reusability, still operate only from a handful of sites worldwide. Even when a launch succeeds, the infrastructure remains tied down. The pad must be inspected, the flame trench repaired, and the fuel tanks refilled. Trucks roll in with new supplies, technicians replace worn-out parts, and new shipments of fuel arrive by rail or ship. It is a cycle of endless maintenance, a rhythm of preparation that continues long after the rocket has vanished into the sky. To maintain this rhythm requires budgets in the billions, ensuring that spaceflight remains one of the most expensive human endeavors. A launch site is a strategic asset. Its location determines the efficiency of launches, its capacity influences national prestige, and its vulnerabilities invite security concerns. Building and maintaining such a site means tying a nation's economy and politics to the infrastructure itself. Decisions about rocket launches are never purely scientific or technological. They are also decisions about supply chains, budgets, and long-term commitments that extend across decades. A plane requires fuel, a runway, and crew, but all these exist in abundance worldwide. A rocket requires a cathedral of steel and concrete, filled with machinery designed to support only one type of vehicle. Every launch is a performance that consumes its stage as it unfolds, requiring constant rebuilding. Until propulsion systems change fundamentally, this tether to Earth will remain. Rockets may soar, but their roots dig deep into the ground, anchored by infrastructure too vast to follow them into the stars. Why reuse doesn't solve the problem. In recent years, the return of boosters has been heralded as a revolution. Watching a towering rocket land upright on a drone ship looks unreal. The economic promise is clear. Instead of discarding a booster after a single flight, why not use it again? Airplanes don't get scrapped after one trip, so why should rockets? Companies like SpaceX have demonstrated that reusing boosters can slash costs dramatically compared to the old model. But even this bold step forward is only a stretch, not a solution. For one thing, reusability does not erase the fuel problem. A reusable booster still requires enormous tanks of propellant to leave the ground. Every time it flies, the same massive amounts of liquid oxygen and kerosene or methane must be produced, stored, and transported. The cost of fuel is smaller than the cost of the booster itself, but it is not negligible, especially when launches are frequent. The rocket equation remains untouched. No matter how many times a booster is flown, it still faces the same brutal trade-off of fuel mass to payload mass. Reuse makes each launch cheaper, but it does not allow rockets to carry vastly more into space. Another hidden limitation is maintenance. A booster is not like a commercial jetliner built for tens of thousands of flights between overhauls. Each landing puts enormous stress on its structure. The engines endure punishing heat, pressure, and vibration. Even with perfect landings, the wear and tear accumulates. After every flight, teams of engineers must inspect, repair, and sometimes replace components before the rocket can fly again. This process is time-consuming and costly, meaning that reusability is never as simple as flying, landing, and refueling. It is closer to refurbishing a race car after every event. The booster may survive, but only through intensive labor and expense. The upper stages remain a bigger problem. While lower boosters can be recovered because they do not reach orbital speed, upper stages almost always burn up or drift in orbit as debris. Catching and reusing them is far more difficult, since they travel much faster and are harder to slow down. Without reusing upper stages, the rocket equation still eats away at efficiency. Even if the bottom half of a rocket can be flown again, the top half is still sacrificed, along with its engines, tanks, and avionics. The dream of a fully reusable two-stage rocket is still mostly unproven, and even if it becomes reality, the underlying physics won't suddenly make rockets capable of hauling massive fleets of colonists into orbit at low cost. Staging and reuse also fail to address the problem of scale. Sending small payloads, satellites, scientific instruments, even small crews to orbit is achievable with today's rockets. But colonization implies something very different. Millions of tons of cargo, habitats, food, water, and people transported across space. The numbers are staggering. Even the most optimistic reusable rocket concepts cannot come close to moving this scale of material. If building a small space station takes dozens of launches and years of assembly, imagine what would be required to build cities on the Moon or Mars. Each kilogram carried requires careful accounting, and every launch still consumes fuel at an industrial scale. Furthermore, the infrastructure required for reusable rockets is just as immense as for expendable ones. Landing pads, drone ships, tracking systems, and refurbishment facilities all add complexity and cost. While the rockets themselves return, the earthbound support remains as heavy as ever. Each booster needs a team, a hangar, and a constant flow of spare parts. This dependence on ground infrastructure limits how often rockets can fly. They cannot yet operate with the frequency and simplicity of airplanes, no matter how many times they are reused. The fundamental issue is that chemical rockets are pushing against the very edge of what is possible with their fuel. The energy density of chemical reactions simply isn't high enough to overcome the rocket equation in a transformative way. Staging reduces dead weight and reusability reduces waste, but neither changes the fact that most of the rocket is still fuel. The steps we have taken are ingenious, but they are only small hacks against a problem that demands a different class of solution. Consider the analogy of a ladder reaching a cliff. Staging and reusability are like adding a few more rungs to the ladder or finding ways to reuse the wood. They help us climb a little higher, but the cliff is still towering above us. To scale it, we would need not just a better ladder, but an entirely new way of climbing. That is why these innovations, as important as they are, cannot by themselves lead to mass colonization. They stretch the possibilities, but they do not break the ceiling imposed by physics. Even with perfect reuse, the costs of mass transport remain astronomical. Every colony ship would need dozens, perhaps hundreds of launches to assemble and fuel. Each of those launches would require its own mountain of infrastructure, its own rivers of fuel, and its own crews of workers. Colonization is not a matter of trimming expenses by half. It is a matter of orders of magnitude. And the rocket equation does not bend by orders of magnitude. Logistics at scale, the unsexy reality of steady supply. Images of colonies on the Moon or Mars are often sleek and clean. Domes of glass glitter under alien skies, machines hum quietly in the background, and settlers walk around in futuristic suits as if their lives are secure. Pop imagination tends to focus on the grand moment of arrival, the first flag planted, the first human footprint in new soil. But a colony cannot survive on symbolism or ceremony. It needs supplies. Tools break, food runs out, air filters clog. Every one of these failures demands a steady flow of replacements from Earth. The real obstacle to long-term survival in space is not just getting there. It is keeping the colony alive once it is built. The history of exploration on Earth offers lessons that apply here. When explorers sailed across oceans to settle new lands, they rarely survived alone. Early colonies depended on constant shipments from their home countries. Food, clothing, nails, lumber and medicines arrived in regular cycles, often months apart. When those supply lines failed, settlements collapsed. The Jamestown colony in Virginia, for example, nearly starved when resupply ships were delayed. The difference between Earth and space is scale. A ship crossing an ocean could carry tons of cargo in its hold. Ships could be built cheaply and sailed repeatedly. By contrast, a rocket can carry only a tiny amount of payload, and every launch is expensive, time-sensitive, and technologically fragile. What was a struggle for wooden ships centuries ago becomes an almost impossible task when the ocean is the vacuum of space. Consider a Mars colony. A crew of even 100 people would need thousands of kilograms of food every year. While some farming could take place in greenhouses, the energy and infrastructure required to grow crops on a hostile planet would be enormous. It would take decades before local farming could even begin to replace imports. Until then, rockets would need to deliver steady shipments of dried food, seeds, fertilizers, and equipment. If even one scheduled resupply failed due to weather, mechanical fault, or funding cuts, the entire colony could be pushed to the brink of collapse. Unlike on Earth, where communities can borrow from nearby towns or forage in the wild, settlers on Mars or the Moon would have no backup options. Every machine that supports life in space will eventually fail. Pumps, valves, filters, and computer systems all degrade under constant use. In the harsh environment of space, repairs are not optional, they are urgent. But many replacement parts are too complex to manufacture locally, at least in the early decades of colonization. A broken pump may require metal smelted under precise conditions or electronics fabricated in ways a small colony cannot replicate. That means the part must be shipped from Earth. The colony, therefore, becomes not a self-sufficient outpost, but a fragile extension of Earth's supply chain. This fragility has already been seen on the International Space Station. The station hosts a small crew supported by one of the most advanced logistical networks ever created. Regular cargo flights bring food, water, scientific equipment, and spare parts. Even then, every resupply is carefully timed, and any delay creates tension. The station has never been truly independent. It is constantly fed by Earth. Scaling this model up to a colony of hundreds or thousands is almost unimaginable with today's tech. Each new settler adds to the logistical burden, multiplying the flow of resources required to sustain life. The more people we send, the more dependent they become on supply lines stretched across space. Every kilogram shipped to orbit is expensive, and every kilogram shipped beyond orbit is even more so. Current launch prices, though falling, still run into thousands of dollars per kilogram. Even optimistic projections that imagine prices dropping below $100 per kilogram still face an unyielding truth. A functioning colony would need millions of kilograms delivered every year. That translates to billions of dollars annually just to keep a small group alive. And this assumes everything goes perfectly, with no accidents, no destroyed cargo, and no political hesitation. If a single launch fails, its payload is lost forever, and the colony feels the shock immediately. Resupply to the Moon is difficult but manageable, with round trips taking days. The launch windows to Mars, however, open only once every 26 months, when Earth and Mars align favorably. That means shipments cannot simply be sent whenever they are needed. They must be planned years in advance. Any emergency in between windows could prove fatal. Imagine a colony's oxygen recycling system failing months before the next launch opportunity. No matter how much money or willpower Earth had, the laws of orbital mechanics would not allow a quick delivery. Another overlooked element is waste. Colonies will generate huge amounts of it: worn-out suits, broken electronics, expired food, and biological waste. On Earth, waste can be managed, recycled, or buried. In space, managing waste requires additional systems, all of which also require spare parts and upkeep. Recycling is often suggested as a solution, but recycling itself consumes energy and machinery, both of which must be imported or maintained. No recycling system is perfect. Every loop leaks material, every process wears down. Over time, without constant replenishment from Earth, the system would collapse. Colonists would know that their survival depends on fragile supply lines they cannot control. This awareness creates constant pressure. Life would not feel like freedom. It would feel like living at the end of a thin, brittle lifeline stretching across space. The romantic image of pioneering independence clashes with the reality of near-total dependence. This is why logistics, though rarely the centerpiece of space discussions, may be the most decisive factor of all. Building the first habitat may be dramatic, but keeping that habitat alive year after year requires discipline, infrastructure, and wealth at a scale far beyond what is usually imagined. The settlers' lives would not be determined by heroic moments of exploration, but by the steady rhythm of supply deliveries, crates of food, boxes of tools, tanks of oxygen. This is the unglamorous truth. Logistics is the heart of survival, and without it, even the most advanced rockets are meaningless. How much habitat is too much? Real mass estimates for a permanent moon base. A base is not just a shelter, it is an entire environment carved out of an alien world. It must provide air, water, food, power, radiation shielding, and medical care. Each of these demands equipment, and each piece of equipment carries mass. Even the simplest design balloons into staggering tonnage once the real requirements are counted. Consider the bare minimum, a pressurized habitat. On Earth, a modest house might weigh between 50 and 100 tons if you include the structure and fixtures. A moon habitat has to do much more than a house. It must hold a breathable atmosphere under pressure while withstanding extreme temperature swings between lunar day and night. This requires thick walls, special seals, and redundant safety systems. Even with lightweight aerospace materials, a single modest module, capable of housing perhaps 4 astronauts, would weigh several tons before adding furniture, storage, or life support machinery. To shelter even a small crew permanently, multiple such modules would be required, connected into a network. Suddenly, the house of a moon base is dozens of tons, even in its most stripped-down form. Now add radiation shielding. The moon has no atmosphere and no magnetic field. Astronauts there are exposed to cosmic rays and solar storms that over time can cause cancer, tissue damage, or acute radiation sickness. Shielding is not optional. NASA studies have shown that several meters of regolith, the moon's loose surface material, would be needed to protect settlers long term. That shielding could be piled on top of habitats, but the equipment to dig, move, and place it must be delivered first. Each lunar bulldozer, excavator, or hauler is not a lightweight rover. To move regolith in bulk, machines must be strong, durable, and reliable. On Earth, even compact construction machines weigh several tons. Sending just one such machine to the moon means dedicating an entire heavy-lift rocket launch. A functioning fleet for excavation and shielding could add dozens or even hundreds of tons to the shipping list. Humans need oxygen, water, and food every day. Recycling systems can stretch supplies, but every closed-loop system leaks material and loses efficiency over time. To support a permanent base, full-scale life support machinery is required, not just the small units used on the International Space Station. Air scrubbers, water recyclers, and waste processors all come with tanks, pipes, wiring, and spare parts. Each unit is heavy, and backups are essential. That means duplication of systems, which doubles the mass. Power supply is another challenge often underestimated. On Earth, electricity flows through grids that can stretch across nations. On the Moon, the base must make its own power. Solar panels are often proposed, and while they can generate energy during the 2-week-long lunar day, they are useless during the equally long lunar night. To survive the darkness, a base needs either enormous energy storage systems, giant batteries weighing tens of tons, or nuclear reactors. A small modular reactor, sized to power a settlement, weighs many tons even before shielding and housing are added. Transporting one safely to the moon is an engineering challenge, and transporting several is a logistical nightmare. Even modest human needs multiply the tonnage. Beds, clothing, medical supplies, food reserves, exercise equipment, computers, and communication hardware all add to the cargo list. A medical bay must be equipped to handle emergencies, which means surgical tools, diagnostic machines, and possibly even a small operating theatre. Without such facilities, a single accident could prove fatal. The more one accounts for these necessities, the more the weight grows. A realistic estimate for even a minimal, continuously occupied base for a dozen people quickly climbs into the hundreds of tons. Rovers for surface exploration, vehicles for hauling supplies, and emergency shelters for evacuations are all vital. Each rover is several tons. Each spare habitat or inflatable shelter is another. The base cannot rely on a single vehicle or structure because in space, redundancy is survival. With every backup, the required mass multiplies. The ISS, designed only for low Earth orbit, not for planetary survival, weighs over 400 tons. And that mass was delivered piece by piece through dozens of rocket launches. Building a permanent lunar base would require similar or greater mass, delivered across far greater distances and assembled under far harsher conditions. And if the goal is not just survival but growth, families, research, industry, the demands expand dramatically. Greenhouses large enough to reduce food shipments would add hundreds of tons. Workshops for repairing or building equipment locally would need lathes, foundries, or even small fabrication plants, each weighing more than can be imagined in a casual sketch. A true permanent base begins to look less like a small camp and more like a small town, with mass requirements pushing into the thousands of tons. Every ton lifted from Earth requires massive amounts of fuel. Even with reusable rockets and heavy-lift vehicles, the cost in energy and resources is staggering. Each launch can carry only so much, and each launch must be carefully timed and supported by ground infrastructure. Delivering the full mass for a moon base would take dozens, perhaps hundreds of missions. Each mission carries risks of failure. A single accident could delay construction for months, if not longer, stranding partial infrastructure on the moon with no way to finish it. This is why realistic estimates for a permanent moon base often shock people. What looks small in an artist's drawing becomes immense when measured in mass. The tonnage of habitats, shielding, life support systems, power supplies, spare parts, medical equipment, vehicles and redundancies is not in the tens, but in the hundreds or thousands. Even before anyone sets foot inside, the base demands a mountain of material to be delivered across space. What we can and can't make with moon dust and Martian soil. The phrase "living off the land" has a romantic quality when applied to space. It suggests pioneers building homes out of local stone, harvesting food from the soil, and crafting tools from whatever the environment provides. On Earth, settlers could hunt, gather, and farm, reducing dependence on shipments from across the sea. Applied to the Moon or Mars, this idea takes on a powerful allure. If we can use the dust and rock already there, maybe we won't need to send so much from Earth. The truth is more complicated. Moon dust and Martian soil are not like the soil in your backyard. They are abrasive, toxic in some cases, and far from ready-made resources. Some things can be made from them, but most of the critical needs of a settlement cannot. Take lunar regolith, the fine powdery dust that covers the moon's surface. It looks soft in photos, but under a microscope, each grain is sharp, jagged, and glassy. Unlike sand on Earth, which has been rounded by wind and water, lunar dust was shattered by constant impacts over billions of years. It clings to surfaces through static electricity, scratches metal, and can damage human lungs if inhaled. Despite these dangers, regolith is rich in minerals. It contains silicon, aluminum, iron, calcium, and small amounts of other elements. In theory, it could be melted into bricks or sintered into concrete-like blocks. Experiments on Earth have shown that by heating regolith simulants with microwaves or concentrated sunlight, you can fuse the grains together into solid slabs. These could be used for building radiation shields or even landing pads. In that sense, the dust has potential. But this potential is limited. Turning regolith into usable material requires enormous amounts of energy. Melting or sintering even a small block means heating it to thousands of degrees Celsius. On the Moon, where power is scarce, generating this heat at industrial scale would be a major challenge. It might be possible for surface structures like walls or shields, which don't require fine tolerances, but not for the precision machinery. You can't make a valve or a circuit board out of raw moon dust. For life support systems, electronics and delicate medical equipment, shipments from Earth remain unavoidable. Martian soil presents a different set of challenges. At first glance, Mars seems more promising. Its soil contains iron oxides, giving the planet its red color, along with other useful minerals. More importantly, Mars has frozen water trapped in the ground, a resource far more valuable than any mineral. By heating or processing the soil, it may be possible to extract water for drinking, oxygen generation, or even fuel production. In fact, NASA's Perseverance rover has already tested a small device called MOXIE, which can turn carbon dioxide from Mars's atmosphere into oxygen. Scaling such technologies up to support human life is still far off, but at least the building blocks exist. Yet Martian soil is also toxic. It contains perchlorates, salts that are harmful to humans. Handling it would require careful processing to avoid poisoning settlers or contaminating crops. The idea of simply planting seeds in the soil, as shown in the Matt Damon film The Martian, is impossible without extensive treatment. Even if detoxified, Martian soil lacks many nutrients plants need to grow. Farming would still depend on importing large amounts of fertilizers or manufacturing them through energy-intensive chemical processes. Living off the land in this case does not mean living directly from the dirt, but transforming it through complex engineering. When it comes to fuels, both the Moon and Mars offer possibilities, but again with limits. On the Moon, regolith contains oxygen locked inside minerals. Through chemical reduction processes, that oxygen can be released. Oxygen is critical not just for breathing, but also as an oxidizer for rocket fuel. The problem is scale. Extracting oxygen from regolith requires heavy processing plants and constant energy input. Setting up such an operation would itself demand massive shipments of equipment from Earth. Mars, with its carbon dioxide atmosphere, is better positioned. Carbon and oxygen can be used to produce methane and oxygen propellants through a process called the Sabatier reaction. Elon Musk's vision of fueling rockets on Mars relies on this. But again, the machinery for carrying out these reactions, storing the fuel, and maintaining the system would all have to be sent from Earth in the first place. The dream of local manufacturing also runs into the limits of precision. Even if metals can be extracted from dust or rock, refining them to aerospace-grade quality is enormously complex. On Earth, steel production involves giant furnaces, carefully controlled chemistry, and supply chains of raw inputs. Aluminum, titanium, and other lightweight metals require electricity and advanced processes. Producing them on the Moon or Mars would not be impossible, but the infrastructure required is closer to that of an entire industrial city than a small outpost. Expecting the first colonists to bootstrap such an industry is unrealistic. For decades, any machinery requiring high precision, whether engines, circuit boards, or medical devices, will still need to come from Earth. 3D printing has been raised as a hopeful solution. In theory, local dust could be turned into feedstock for printers, which could then fabricate parts on site. Early experiments have indeed shown that regolith simulants can be bound into simple shapes. But there is a huge gap between printing a block or a simple pipe and printing a complex load-bearing engine part. Printers capable of that level of sophistication require exacting feedstock, advanced nozzles, and software. They are also prone to breakdowns and would need a constant flow of imported replacement parts themselves. In practice, 3D printing may help with non-critical structures like spare tiles or housing segments, but it cannot replace the industrial base of Earth. On Mars, the presence of water ice suggests that greenhouses could eventually be built. On the Moon, the lack of atmosphere and liquid water makes farming even harder, though hydroponics is possible if water can be recycled efficiently. But both scenarios require large habitats, artificial lighting, fertilizers, and constant care. Growing enough to feed even a dozen people consistently would require facilities weighing dozens of tons, plus constant inputs. The fantasy of settlers planting crops in alien dirt overlooks the fact that Earth's soil is the product of billions of years of biology. Without that hidden richness, soil is just empty dust. Growing enough without Earth's biosphere. We grow crops on Earth every day, so why not simply build greenhouses in space and repeat the process? Because food production is one of the hardest problems to solve outside Earth. On our planet, a vast, stable biosphere quietly handles millions of tiny processes that keep plants alive. In space or on another world, every one of those processes must be recreated artificially, and none of it comes free. The first hurdle is light. On our planet, the sun provides a steady source of energy for plants, filtered by the atmosphere in ways that make it gentle enough to sustain life. On the Moon, there are 2 weeks of constant daylight followed by 2 weeks of darkness. A greenhouse sitting there would either overheat in endless sun or freeze in endless night. On Mars, the day-night cycle is closer to Earth's, but the sunlight is much weaker, about half the intensity we enjoy here. That means artificial lighting becomes essential, powered by electricity from solar panels, reactors, or other energy sources. Suddenly, the simple act of photosynthesis requires a chain of machines and power systems. Water is another challenge. On Earth, rain cycles through the atmosphere and returns to the soil almost without thought. In space, every drop must be transported or recycled. A tomato plant might need 2 liters of water per week. Multiply that by hundreds or thousands of plants, and the numbers add up quickly. Recycling systems can reclaim some of it through condensation, but no system is perfect. Water is lost through leaks, evaporation, or absorbed into growing mediums that must eventually be replaced. While scientists have proven that plants can grow in hydroponic or aeroponic systems with careful recycling, scaling these setups to support an entire crew or colony would demand extraordinary care and constant supplies of replacement parts. Then there are nutrients. Plants don't live on water and light alone. They require nitrogen, potassium, phosphorus, and a long list of trace minerals. On Earth, these are delivered naturally through soil ecosystems and fertilized by bacteria, fungi, and decomposing organic matter. On Mars or the Moon, there is no soil in this sense, just dust or rock with little biological content. Fertilizer would need to be imported, manufactured locally through complex chemical processes, or recycled endlessly from human and plant waste. Each option has drawbacks. Importing nutrients is costly and unsustainable. Manufacturing them from raw material requires heavy equipment and energy. Recycling has limits. Without a steady nutrient supply, crops would weaken, yields would drop, and the food system would eventually collapse. On Earth, the magnetic field and atmosphere shield plants from high-energy particles. In space, radiation can damage plant DNA, slow growth, and reduce yields. Shielding greenhouses with thick layers of soil or water is possible, but this adds enormous mass to any structure. An alternative is to grow plants underground with artificial light, but that circles back to the energy problem. The more protection you give crops, the more power you must spend to keep them alive. People need a balanced diet with a mix of calories, protein, fats, vitamins, and minerals. It is not enough to grow just 1 or 2 hardy plants. A colony would require a wide range of crops: grains for carbohydrates, legumes for protein, fruits and vegetables for vitamins, oils for fats. Each plant has its own needs for light, water, and nutrients, complicating the farming system further. On Earth, agriculture depends on massive networks of fields, specialized machinery, pollinators like bees, and centuries of selective breeding. Rebuilding even a fraction of that complexity in a small habitat is a monumental task. A small hydroponic experiment in a laboratory or space station can show that lettuce or radishes will grow, but feeding 10 people continuously requires hundreds of square meters of growing space. Feeding 100 people requires thousands. Each square meter of plants demands lighting, water delivery, air circulation, and temperature control. On Earth, a bad harvest in one region can be offset by imports from another. In space, failure could mean starvation. Some researchers have suggested supplementing plant growth with algae or single-cell proteins. Algae can produce food quickly in small volumes of water, and microbial protein can be grown in bioreactors. These methods may provide important nutrients, but they are far from the comforting image of fields and orchards. A diet made mostly of algae or microbial paste could meet calorie needs, but would do little for morale or mental health. Humans are deeply connected to food as culture and comfort, not just as fuel. Life in a harsh, isolated environment would be made harder if meals became repetitive and joyless. The question of pollination also arises. Many plants rely on insects to transfer pollen, and recreating this system off Earth would require either importing insects, an ecological challenge in itself, or developing machines to handle pollination. Hand pollination is possible, but it is labor-intensive and unrealistic for large farms. Without these processes, some staple crops cannot reproduce effectively. Finally, food storage and safety present another layer of difficulty. On Earth, refrigeration, preservatives and trade routes ensure a steady food supply even when local crops fail. Off Earth, storage would be limited and every gram of food would be precious. If a crop developed mold or was contaminated, the loss could be devastating. Managing waste streams, ensuring hygiene and preventing the buildup of harmful microbes would demand constant vigilance. For now, space agencies rely on sending packaged meals from Earth, carefully measured to meet nutritional needs. But this method scales poorly. As the number of people in space grows, so does the weight of food that must be launched. The food problem is not just about growing plants. It is about recreating an entire biosphere in miniature, something humanity has never truly done. Power deserts, energy realities on the Moon and Mars. Energy drives heating, cooling, air circulation, water recycling, communications, and the growing of food. Without it, even the most advanced life support systems collapse within hours or days. The Moon and Mars are not rich with natural power waiting to be tapped. They are instead power deserts. Unlike Earth, which rotates every 24 hours, the Moon rotates once every 29.5 days. This means a lunar day lasts about 2 weeks, followed by a lunar night that lasts just as long. During the daytime, solar panels can harvest abundant sunlight. But when the long night sets in, temperatures plunge to below -170 degrees Celsius, and the surface is plunged into total darkness. Surviving that period requires storing vast amounts of energy during the day or switching to another source altogether. Storing 2 weeks' worth of power in batteries at the scale needed for a base is not realistic with today's technology. The largest battery systems on Earth are designed to smooth out short-term power fluctuations, not keep entire colonies alive in unbroken darkness. A small modular reactor could provide steady energy regardless of day or night. But these reactors are not simple machines. They are heavy, complex, and politically sensitive. Launching one safely through Earth's atmosphere requires extraordinary precautions. Once on the Moon, it would need shielding, cooling systems, and a crew capable of maintaining it. Even then, reactors have limited lifespans, and replacement parts would need to be shipped from Earth. Nuclear energy could provide a bridge for lunar operations, but it is not the easy fix it is sometimes portrayed to be. Unlike the Moon, Mars days are about 24.6 hours, close to Earth's rhythm. That sounds convenient, but the sunlight on Mars is only about 43% as strong as on Earth. Dust in the atmosphere further reduces this, and the frequent dust storms can last for weeks or even months, blotting out much of the sun. Solar panels that might work well in clear conditions suddenly produce only a fraction of their normal output. A colony, depending on solar power alone, would need vast arrays of panels, spread across the surface, and enormous energy storage systems to endure storm seasons. Mars is a cold world, with average surface temperatures around -60 degrees Celsius. Habitats must be constantly warmed, not just for comfort, but to prevent machinery from seizing and pipes from freezing. Heating requires steady power, which cannot pause during storms or long nights. On the Moon, the issue is even more extreme during the 2-week-long nights. Every watt of heat would come at the cost of consuming precious energy reserves. Wind energy is often raised as a possibility on Mars, but the thin atmosphere makes it nearly useless. Winds on Mars can reach high speeds, yet the density of the air is only about 1% of Earth's. Even the most violent Martian storms carry less force than a light breeze on Earth. Wind turbines would generate very little usable power, making them impractical. Geothermal energy, which powers some systems on Earth, is uncertain on the Moon or Mars. While Mars has signs of past volcanism, the available heat near the surface is weak, and drilling for geothermal energy in harsh, remote environments would be difficult and costly. All of this points to a harsh truth. Energy, not distance, may be the greatest barrier to sustainable colonies. On Earth, power systems are supported by huge infrastructures, grids, pipelines, refineries, and repair crews. In space or on another planet, there is no backup. Every system must be self-sufficient, redundant, and robust enough to withstand long periods without outside help. Building such a system is far harder than simply planting solar panels on alien soil. On Earth, power lines stretch for hundreds of miles. On the Moon or Mars, cabling must be insulated, buried, or shielded to protect it from radiation, dust, and extreme temperatures. Solar farms might be located kilometers away from habitats to maximize exposure, meaning transmission losses and more infrastructure. Every meter of cable or pipe must be shipped, built, or manufactured, adding to the burden. There are concepts for solving these problems in more creative ways. Some have suggested orbiting solar stations that beam power down to colonies with microwaves or lasers. In theory, these satellites could bypass long nights or storms by staying in continuous sunlight. But the technology is untested at the scale required, and the efficiency losses in transmission are high. Building and maintaining such satellites would itself be an enormous engineering feat. Others have proposed networks of small reactors combined with solar panels, creating redundancy and backup. Yet even with redundancy, the logistical problem remains. Spare parts, skilled operators, and maintenance cycles all depend on Earth. Energy is the heartbeat of every other system, and the Moon and Mars are worlds that resist it at every turn. Power there is not abundant or easy. It is fragile, limited, and must be coaxed into existence with massive effort. Manufacturing beyond Earth. Despite decades of progress in spaceflight and robotics, the ability to manufacture complex goods beyond Earth is still little more than a mirage. On Earth, industry thrives within a vast web of resources, infrastructure, and workers. Raw materials are mined, refined, and processed in specialized plants before being transported to factories. Components are made in different places and then assembled together. Supply chains stretch across the globe, allowing for efficient specialization. A smartphone, for example, requires glass made in one country, chips produced in another, and metals mined in yet another. All of this is coordinated by millions of people and countless machines. Now imagine stripping all of that away and trying to replicate it on a barren planet or in orbit, with only a handful of astronauts and limited machines. The manufacturing experiments that have been carried out in space so far are modest. A few 3D printers have been tested aboard the International Space Station, producing small plastic parts like tools or simple brackets. These experiments proved that additive manufacturing works in microgravity and can be useful in emergencies. But these printers rely on feedstock, plastic filament, that still has to be launched from Earth. They also produce only small items. Metal 3D printing is far more challenging, as it requires high temperatures and careful control over material properties. Even on Earth, where conditions are stable, high-quality metal printing is a specialized process that demands advanced facilities. Factories on Earth depend heavily on precision. Machines are built and calibrated with extreme accuracy to ensure that parts fit together perfectly. Dust, vibration, or temperature changes can ruin a manufacturing process. On the Moon or Mars, the environment is hostile to precision. Dust clings to surfaces, temperatures swing wildly, and radiation affects electronics. Protecting machinery inside sealed habitats is possible, but that would consume valuable pressurized space and require life support for the machines as much as for people. Manufacturing consumes large amounts of power, especially when melting or refining materials. Smelting metal ores, for instance, requires sustained high heat. On Earth, this is achieved with giant furnaces powered by coal, natural gas, or large electrical grids. A single industrial process could consume more energy than an entire colony can produce, making large-scale manufacturing impossible with current capabilities. To build complex machines, one needs access to a wide range of elements: iron, copper, aluminum, silicon, rare earths, and more. Earth's industries rely on an entire planet's worth of resources. The Moon has some valuable elements, but they are scattered and mixed in ways that are difficult to mine. Mars may have a broader selection, but extracting and refining them would demand heavy machinery, chemical plants, and workers. Mining is not a simple matter of digging up soil. Ore must be crushed, processed, and chemically treated before it becomes usable metal. Each of these steps requires equipment and chemicals that must themselves be manufactured. It is a chain of dependency that cannot be easily bootstrapped on alien worlds. Even if raw materials could be gathered, turning them into advanced products is another leap. A simple steel beam or aluminum sheet might be achievable in the long term, but a rocket engine, a solar panel, or even a reliable circuit board involves processes that depend on dozens of specialized steps. For example, a microchip requires facilities cleaner than an operating room, with tools that etch circuits at scales smaller than a virus. These facilities cost billions of dollars to build on Earth and rely on global supply chains. The idea of reproducing such factories on Mars or the Moon is incredibly far beyond current capability. Some suggest that robotic automation could solve the labor problem. Robots, in theory, could handle mining, refining, and manufacturing tasks without needing air or food. But robots are not independent workers. They are tools designed for specific environments. On Earth, even advanced factories depend on armies of technicians and engineers to maintain machines, troubleshoot failures, and adjust processes. In space, robots would need to function without such dense support. They would also need to be more versatile than anything that exists today, capable of adapting to unfamiliar problems without constant human oversight. That level of autonomy is still being worked on. The logistics of simply setting up a factory are also overwhelming. On Earth, building a new factory might involve shipping heavy machinery by road, sea, or rail. A single industrial furnace could weigh tens of tons. Even if modular designs were possible, the number of launches required would be staggering. The cost of transporting the first factory components might exceed the cost of simply resupplying a colony from Earth for decades. For now, the most realistic vision of off-world manufacturing is limited to support roles. Small-scale production of replacement parts, simple tools, or structural elements may reduce dependence on Earth. Printing a spare wrench or bracket could save a mission. Producing building materials like bricks from lunar dust or Martian soil is under study and may help with constructing habitats. But these are small, specialized tasks, not full-fledged industries. They help stretch supplies, but do not eliminate the need for Earth-based support. The larger vision, that of cities in space building their own rockets, electronics, and machines, is still far away. To reach that point, humanity would need not only breakthroughs in manufacturing, but also in energy, robotics, and materials science. More importantly, it would require an entire economic system in space to justify the massive costs. Industry grows where there are markets, workers, and demand. So far, those conditions exist only on Earth. Repair, redundancy, and the fragility of high-tech life support. spacecraft and stations already use backups for nearly everything. The International Space Station carries multiple oxygen generation systems, several ways to scrub carbon dioxide, and manual emergency options in case the automated ones fail. But redundancy multiplies weight. An extra carbon dioxide scrubber might weigh a few hundred kilograms. Extra oxygen tanks add hundreds more. A full duplicate of a system can double the mass. For short missions, this is manageable. For permanent colonies, the scale of redundancy becomes staggering. A base designed for a dozen people may need not just 1 or 2 layers of backups, but entire parallel systems waiting to take over when the first inevitably falters. Repair is another side of the problem. Spare parts have to be stored, and specialized tools must be available. Each component has its own maintenance cycle. On Earth, repair is supported by massive supply chains, skilled technicians, and factories producing replacement parts. Off-world, those support networks do not exist. If a specialized pump fails on Mars, the only options are to have a replacement already on hand, or to improvise one using whatever tools and materials are available. Neither path is simple. Carrying replacements for every part of every machine quickly balloons the cargo weight to impractical levels. Apollo missions had backup oxygen systems and manual re-entry procedures. The space shuttle carried multiple computers running in parallel, with software designed to cross-check itself. The ISS crew spends a large portion of their time maintaining and repairing life support. Even with constant resupply from Earth, breakdowns are frequent. Fans stop working, valves clog, and water recycling units fail. Each incident requires hours of troubleshooting and often waiting for spare parts to arrive on the next cargo ship. Now extend that reality to a base that cannot rely on a quick delivery. The fragility becomes far more visible. A kilogram of spare parts is a kilogram less of food, water, scientific equipment, or building material. Mission planners are forced to make choices: which systems deserve full duplication and which must rely on fewer backups. Each compromise increases the risk that one unlucky sequence of failures could lead to disaster. Astronauts are trained in many areas, but they cannot be experts in every specialized system. Fixing a broken pump might require knowledge of fluid mechanics, electronics, and machining. On Earth, a team of specialists would handle it. In space, the crew must improvise with limited expertise, often under extreme stress. Training for every possible failure is impossible, so the crew must rely on instructions from Earth, yet those instructions are delayed by up to 20 minutes each way on Mars. A real-time back-and-forth conversation for solving a failure becomes drawn out, eating into precious time when systems may already be on the verge of collapse. A life support system may have 2 or 3 backups, but they all rely on the same power supply. If the power grid fails, all the backups fail with it. True redundancy requires independent systems, separate energy sources, separate storage, and even separate habitats. This multiplies the scale again. Instead of 1 colony module, there might need to be 2, with full life support in each. Instead of 1 power system, 2 must be built. Each new layer of safety adds dramatically to mass, complexity, and cost. High-tech life support is not a single sleek system that works forever. It is fragile, layered, and endlessly demanding. Closed-loop systems and their unknowns. A closed-loop system in space is often described as the holy grail of settlement. The idea is appealing. Instead of constantly shipping food, water, and oxygen across millions of kilometers, you design an environment where everything is reused. Waste becomes input. Inputs cycle endlessly, and nothing is truly lost. On Earth, we can take this for granted because our biosphere does this job for us. The air you breathe out becomes fuel for plants. The water you drink eventually flows back into clouds. Nutrients cycle through soils, rivers, and oceans. The planet does the hard work invisibly. In orbit, on the Moon or on Mars, there is no such hidden machinery. Every molecule has to be tracked, cleaned, and put back into service by machines or tightly controlled ecosystems. Humans exhale carbon dioxide, sweat salts, and produce organic waste. All of that must be broken down into safe, usable resources again. Plants can absorb some of it, but they too produce waste and require their own conditions. Machines can filter and separate gases, distill water and capture carbon, but they are never perfect. On Earth, losses disappear into the background of an enormous biosphere that restores equilibrium. In space, every lost gram of oxygen or nitrogen is a permanent loss unless replaced. Over months or years, even minuscule inefficiencies accumulate. This is why the dream of a perfectly closed system remains more of an engineering ambition. Experiments have been tried. One of the most famous was Biosphere 2 in Arizona, built in the late 1980s. The goal was to house 8 people inside a giant sealed dome filled with plants, animals, and carefully designed ecosystems. The enclosure was meant to run for 2 years without outside resupply, recycling everything internally. The outcome was mixed at best. Oxygen levels fell dangerously low, eventually requiring outside intervention. Nutrient balances shifted unpredictably, favoring some organisms over others. Tiny microbes in the soil consumed more oxygen than expected, throwing the system off balance. While the experiment did not fail completely, people survived, crops grew, and recycling worked to some degree. It highlighted how complex Earth's biosphere truly is, and how difficult it is to replicate even a small slice of it. The International Space Station heavily recycles water. Astronauts drink water that has been filtered from urine, humidity, and other waste streams. Air is scrubbed of carbon dioxide using chemical systems, and oxygen is sometimes generated from splitting water molecules through electrolysis. But even with decades of refinement, the ISS does not run fully closed. Resupply ships regularly bring water, oxygen tanks, and food. The recycling systems reduce how much is needed, but they cannot eliminate the dependence. The unknowns multiply when considering decades of use. Plastic tubing exposed to radiation becomes brittle. Even steel can corrode or fatigue under constant cycling. On Earth, when a machine breaks, you replace the part. In a true closed system, every replacement would need to be manufactured from within. That means raw materials, processing equipment, and fabrication tools, all of which themselves must be maintained. A closed loop is not just about recycling water and air, it is about recycling the infrastructure that does the recycling. This recursive requirement quickly spirals into daunting complexity. Plants are not simple. They are sensitive to light levels, nutrient balance, humidity, and pollination. Over time, populations can collapse from disease, genetic drift, or subtle imbalances. In a greenhouse on Earth, farmers can adjust soil, add fertilizers, introduce predators for pests, or replant from outside seed stocks. In a sealed Martian dome or lunar habitat, these safety valves are unavailable. A single fungal outbreak could wipe out an entire crop cycle. That means redundancy is required, multiple crop types, backup seeds, extra lighting systems. Even microbial communities, often overlooked, are crucial. On Earth, soil microbes break down waste into nutrients plants can use. In controlled environments, their activity is unpredictable. Some consume oxygen, as seen in Biosphere 2, or produce unwanted byproducts. Others might evolve under the artificial conditions, changing how they interact with the ecosystem. A closed loop that relies on biology is not static. It is dynamic and sometimes unstable. Managing it requires constant observation and intervention, something that may not be feasible for a small crew stretched thin. Engineers sometimes argue for purely mechanical solutions: filters, scrubbers, chemical reactors. These can be modeled, maintained, and designed with redundancy. But even mechanical systems are vulnerable to the entropy tax. Catalysts lose their activity, bearings wear down. The dream of machines that endlessly recycle without wear or input ignores the realities of material science. Space dust, radiation, and thermal stresses make degradation faster, not slower. Recycling systems that work for a handful of astronauts in orbit also may not scale to dozens or hundreds of settlers on Mars. A larger population means more waste streams, more air volume to manage, and more food to produce. Systems that seem manageable at one scale may become unstable at another. Small inefficiencies multiply as the loop gets bigger. This makes the path to self-sustaining colonies uncertain. What works in a test chamber or space station module may not translate to a city-sized dome. Some researchers propose hybrid systems, where recycling is partial and supplemented by outside supply. For example, oxygen might be mostly recycled, but occasionally topped up with local production from electrolysis of lunar ice. Food could be grown partly indoors, but regularly supported by imports. These approaches are less ambitious, but far more realistic. A closed loop in the absolute sense does not yet exist, and may never exist in a form that supports large populations. Humans have always lived in open systems, able to step outside for fresh air or gather food from the environment. In a closed loop, every action is tied to the system's stability. Using too much water, mishandling waste, or even altering the balance of light in a greenhouse can ripple across the loop. The sense of fragility may weigh heavily on settlers, making life less about exploration and more about maintenance. Living inside a machine that must be perfect at all times could reshape how people view freedom, community, and survival. The idea of closed-loop systems will continue to be researched because the alternatives are also daunting. Progress will likely come incrementally. Better water recycling, more reliable carbon scrubbers, more resilient crops. But the leap from partial recycling to full autonomy is still uncharted territory. We do not yet know if a system can be built that truly runs for decades without outside help. And if such a system is ever achieved, it may look less like a tidy loop and more like a messy patchwork of overlapping processes, each compensating for the failures of another. Radiation, the invisible barrier. There are two main sources of radiation in space. One comes from our own star. The sun releases constant streams of charged particles called the solar wind. Most of the time, this wind is relatively weak. But occasionally, the sun flares. During a solar storm, vast clouds of energetic particles shoot outward, capable of reaching Earth in hours. When they hit satellites, they can fry electronics. When they hit humans without protection, the exposure can be lethal. Astronauts caught outside during a major solar storm would need to quickly retreat to a shielded chamber or risk severe radiation sickness within hours. The second source is even more difficult to handle: galactic cosmic rays. These are particles, often protons and atomic nuclei, accelerated to near-light speeds by distant supernovas and black holes. They strike with energies far higher than solar radiation, and they cannot be predicted or avoided. Shielding against these invisible threats is a matter of physics and mass. Radiation can be blocked, but only by placing enough material between the source and the target. On Earth, this is easy. We have kilometers of air and rock above us. In space, it is nearly impossible. Every kilogram of shielding must be launched at tremendous cost. To give astronauts the same level of protection as standing on Earth would require walls several meters thick made of water, concrete, or metal. Such shielding is not practical. Designers compromise, using thinner layers of aluminum or specialized plastics to reduce exposure. These measures help, but they cannot eliminate the risk. On the International Space Station, astronauts receive doses of radiation hundreds of times higher than people on the ground. The doses are not immediately fatal, but over time, they increase risks of cancer, cataracts, and neurological damage. Missions lasting 6 months already push against safety limits. A round trip to Mars, lasting 2 to 3 years, would expose astronauts to far more. Without adequate protection, the journey itself could cut years off their lives or leave survivors with chronic health problems. The Moon is even worse in some respects. With no atmosphere and no magnetic field, the lunar surface is directly exposed. During Apollo missions, astronauts were fortunate that no major solar storms struck while they were on the surface. A single severe event could have been deadly. Ideas for shielding have been tested, but each has flaws. Using thick layers of metal seems straightforward, but metals can create secondary radiation when struck by cosmic rays, sometimes making the problem worse. Plastics rich in hydrogen atoms are more effective because hydrogen can absorb charged particles without producing as much secondary radiation. Water is also excellent, and some designs propose using tanks of water around crew quarters. In principle, fuel, water, and other consumables could double as shielding if arranged properly. But again, the issue is mass. Every extra ton of water or plastic makes the rocket harder to launch and more expensive to send. Settlers could pile regolith on top of their habitats to create a protective barrier. Several meters of regolith would dramatically reduce exposure, but implementing it is no small task. Moving and piling tons of soil would require heavy machinery, power, and time. Until such shielding is in place, settlers would remain vulnerable. The first crews would need temporary solutions. Some engineers suggest magnetic or electric shields, mimicking Earth's magnetic field on a smaller scale. The idea is to generate a bubble of charged particles that deflect incoming radiation. In theory, it could protect a spacecraft without requiring tons of material. In practice, creating and maintaining a powerful enough field is far beyond current technology. The fields required would be enormous, demanding massive amounts of energy and posing risks to onboard electronics and even the crew. For now, these remain futuristic concepts, more at home in research papers than practical mission plans. The uncertainty of radiation damage adds another layer of difficulty. Short-term effects like radiation sickness are well understood, but the long-term consequences of constant low-dose exposure in space are less clear. On Earth, we study radiation workers, medical patients, and survivors of nuclear accidents to understand health effects. But those cases do not perfectly match the conditions of space. Cosmic rays, for example, are far more energetic than most forms of radiation encountered on Earth. Their biological effects may be unique, and there is evidence that they can penetrate deep into tissues, causing clustered DNA damage that is especially hard for cells to repair. This makes predictions uncertain. Are the risks tolerable for multi-year missions, or would they gradually degrade cognitive and physical abilities? The answer is still unknown. For space settlement, this uncertainty is more than an academic question. A colony on Mars or the Moon would not only house adults in good health, but potentially children. Developing bodies are far more sensitive to radiation. Generations exposed to elevated cosmic radiation could face increased cancer rates, genetic mutations, or developmental issues. Shielding may reduce the risks, but unless it can be made nearly as effective as Earth's natural defenses, the long-term health of such a population remains in doubt. Unlike a fire or mechanical failure, there is no alarm to sound, no quick fix to apply. The danger is silent and unavoidable. People might adapt, accepting it as part of their environment, much like early sailors accepted scurvy and storms. But it may also discourage long-term habitation unless real solutions are developed. Without protection from the relentless storm of particles in space, every other system becomes irrelevant. The settlers may have food, air, and power, but they would still be aging faster, risking illness and gambling with unseen forces. Low gravity slow damage, bones, brains, and blood. Astronauts in Apollo footage appear to hop and glide as though the rules of physics had loosened. But beneath that playful image lies a serious problem. Human bodies evolved in one gravity. Our muscles, bones, and even our blood circulation are tuned to the pull of Earth. Remove or reduce that pull, and systems begin to unravel in ways that are not immediately visible, but are deeply harmful over time. Bones are among the first casualties. On Earth, every step we take puts weight on our skeleton, keeping bones dense and strong. Gravity acts like a constant training program, stressing the bones so they remain sturdy. In orbit or on the Moon, where gravity is only 1/6 of Earth's, or on Mars with 1/3, that stress is far weaker. The body adapts, but in the wrong direction. Without the usual pressure, bones start to shed minerals. Calcium leaches into the bloodstream, leaving bones more fragile and prone to breaks. Measurements from astronauts show losses of 1 to 2% of bone mass per month in weight-bearing areas like the hips and legs. That is far faster than osteoporosis on Earth, which usually develops over decades. For long missions, the numbers become alarming. A year in space could strip away over 10% of bone density, enough to make ordinary falls dangerous. Muscles follow a similar path. On Earth, standing up, walking and lifting all require work. In microgravity, floating requires none. Even in the partial gravity of the Moon or Mars, daily activities demand much less effort than we are built for. Muscles, like bones, respond by shrinking. Strength declines, endurance fades, and coordination suffers. On the International Space Station, astronauts exercise for hours each day using resistance machines, treadmills, and stationary bikes. These routines slow the loss, but do not stop it. Returning astronauts often need weeks to rebuild muscle and balance, even after 6 months. In a settlement where people might spend years, or even their entire lives in low gravity, the long-term outcome is unknown. Will muscles ever fully adapt, or will they remain permanently weakened? Nobody yet knows. Gravity also shapes how fluids move through the body. On Earth, blood and other fluids are pulled downward, pooling in the legs and feet. In orbit, without gravity, fluids redistribute, moving toward the chest and head. Faces puff up, sinuses clog and legs thin. The shift might seem cosmetic, but it places pressure on delicate systems. Some astronauts have reported lasting vision problems, believed to be caused by increased pressure inside the skull. This condition, called spaceflight-associated neuroocular syndrome, suggests that the brain and eyes are not built to handle fluid balance without gravity's pull. On Mars or the Moon, with weaker but not absent gravity, the effect may be somewhere between Earth and spaceflight, but we do not yet know how damaging it could be over years. The heart, no longer working as hard to pump blood against gravity, begins to weaken. Muscles in the heart shrink and blood volume decreases. Back on Earth, astronauts often feel dizzy or faint when standing, because their hearts and blood vessels have forgotten how to respond. On the Moon or Mars, settlers would not return home quickly. They would live in an in-between state, where circulation never fully adjusts. What this does to long-term cardiovascular health is uncertain, but the risks are real. The brain too may not escape unscathed. Research shows that time in microgravity changes the structure of the brain. MRI scans of astronauts before and after missions reveal shifts in grey matter and white matter. Some areas of the brain expand, others shrink. The exact meaning of these changes is still being studied, but the possibility that low gravity could alter cognition, memory, or motor skills raises serious concerns. If settlers need to make critical decisions under stress, degraded brain function could be life-threatening. Even mild impairments could erode the safety of missions over time. The International Space Station serves as a laboratory for microgravity effects. Most astronauts stay 6 months. A few have stayed close to a year. Even within this span, bone loss, muscle weakness, cardiovascular deconditioning, and eye problems emerge. Longer stays have not yet been tested in humans. Missions to Mars would require at least 2 to 3 years, with partial gravity on the surface and microgravity in transit. Colonies would mean lifetimes spent away from Earth's pull. The experiment has barely begun, and the early results are troubling. If humans were to raise families on Mars or the Moon, their bodies would develop under weaker gravity from the start. Bones might never reach Earth normal density. Muscles might remain smaller, and hearts weaker. Cognitive development could be affected by fluid shifts and changes in brain structure. No one can say with certainty how severe these effects would be, but they would likely make returning to Earth impossible for those born in low gravity. Generations might evolve into a separate branch of humanity, adapted to weaker worlds, but too fragile for the one they left behind. Countermeasures have been proposed, but none are simple. Exercise machines help slow bone and muscle loss, but they require time, equipment, and discipline. They cannot perfectly mimic the constant effect of gravity. Artificial gravity, created by spinning spacecraft or rotating habitats, is often suggested as a solution. In theory, rotation could simulate Earth's pull through centrifugal force. In practice, Building and spinning massive structures safely is a huge engineering task, one far beyond what has yet been built. Smaller rotating sections could provide partial relief, but they come with technical and cost challenges. On planetary surfaces, there is no way to change the pull of the planet itself. Mars will always have 1/3 of Earth's gravity, the Moon 1/6. The only choice is to adapt or build rotating habitats separate from the surface. Adaptation is possible, but adaptation may come with a price. The human body is flexible, but flexibility has limits. Too much bone loss, too much muscle weakness, and too much fluid imbalance lead to disease. Even if settlers accept frailty as the price of living on another world, they still need to remain functional enough to survive harsh environments, operate machinery, and manage emergencies. Weakness could mean the difference between fixing a failing system in time or watching a habitat fail. A community cannot run on people who are too fragile to perform heavy work. Reproduction and childhood off-world. No human has ever conceived or given birth in space. The subject has barely been tested even with animals. A few studies have flown small mammals, insects and fish in space, but almost all were short-term and incomplete. In some cases, fertilized eggs developed normally for a time, but in others, embryos failed to grow properly or showed abnormalities. None of these studies answers the central question: what happens to mammals, and especially humans, when an entire reproductive cycle unfolds beyond Earth? On Earth, reproduction and pregnancy rely on finely tuned biological processes. Cells divide, embryos implant, organs form, and the body supports growth over months. All of these steps evolved in one gravity. Remove or weaken that constant downward pull, and it is not clear whether the same processes will continue smoothly. For example, fertilized eggs in mammals must move through fallopian tubes, guided partly by tiny hair-like structures and fluid flow. Gravity likely plays a role in directing that movement. Without it, the journey could be disrupted, leading to failed implantation or abnormal development. Even if implantation succeeds, pregnancy is a delicate balance. The mother's circulation, bone health, and nutrient flow are all stressed. On Earth, the body compensates. In space, fluid shifts toward the head, bone mass declines, and blood volume drops. Would a pregnant body in microgravity be able to deliver enough nutrients and oxygen to a fetus? Would low gravity change how organs form, how bones grow, or how brains develop? These are not hypothetical curiosities. They are central to whether humans can ever become a spacefaring species. If conception and pregnancy occur under 1/6 or 1/3 of Earth's gravity, the fetus may adapt differently from the start. Bone growth could be weaker, muscle development slower, and organ positioning altered. What results is not known because it has never been tested. But the possibility exists that children born on Mars or the Moon might be fundamentally different in physiology. They could survive in their home gravity, but struggle if brought to Earth later. Developing embryos are especially vulnerable to DNA damage. On Earth, radiation exposure is tightly controlled during pregnancy. Doctors warn against X-rays and prescribe caution even with mild risks. In space, exposure is constant and unavoidable. For an embryo, such damage could mean miscarriage, birth defects, or developmental delays. Even if pregnancy continued to term, the long-term risks for childhood cancer or genetic instability would be high. The growth of bones, muscles, and organs is shaped by load and stress. Children's skeletons strengthen as they learn to crawl, walk, and run under Earth's gravity. On Mars or the Moon, the weight is lighter and the challenge is less. The result might be weaker bones that never reach Earth normal density. Muscles, too, might remain smaller and cardiovascular systems less robust. Generations could grow into a population unable to safely visit or return to Earth, effectively locked into their planetary cradle. The brain grows rapidly in childhood, and environmental factors shape its pathways. If fluid shifts in low gravity increase pressure inside the skull, as they do in adults, what would this mean for a developing brain? Could it change memory, learning, or behavior? The social environment, too, would be unprecedented. Growing up in confined habitats, under artificial light, surrounded by machinery and a small community, would be very different from childhood on Earth. Isolation, lack of natural spaces, and constant awareness of danger could shape culture and psychology in ways we cannot yet predict. Testing reproduction in space is fraught with moral questions. Sending animals is controversial, and sending humans is even more so. The risks are high, and the unknowns are vast. No agency has yet dared to attempt human conception beyond Earth, partly because of these ethical barriers. But without data, the dream of settlements remains hollow. A colony cannot survive on imported adults forever. Eventually, birth and childhood must occur, or the settlement will fade when its first generation dies. Some have suggested possible workarounds. Artificial gravity might provide Earth-like conditions for pregnancy and growth. A rotating nursery could shield developing children from the worst effects of low gravity, at least during critical stages. Nutritional supplements, exercise regimes, and medical monitoring might help offset other risks. But these are partial measures, untested in practice. The deeper truth is that we cannot yet say whether humanity can safely reproduce away from Earth. The assumption often made that settlers on Mars will raise families and grow into a new society rests on groundless optimism. It assumes that biology will bend without breaking, that evolution's fine-tuned processes will continue under alien conditions. But until experiments are done, these remain guesses. And the guesses lean toward difficulty, not ease. Every system in the human body is interconnected, and disturbing one element can ripple across development in ways too complex to predict. On the one hand, we have the technical ability to send rockets, build habitats, and maybe even keep adults alive for years on Mars or the Moon. On the other, we lack the most basic knowledge of whether those adults could ever raise children there. It is as if we have built the tools for a house, but do not know whether fire, air, and water exist in the neighborhood. Without that knowledge, the dream of becoming a multi-planet species remains incomplete. The image of children playing under a low Martian sky or bouncing in the weak gravity of the Moon is powerful, but right now it is only an image. The reality could be far harsher. Until we confront these possibilities with careful study, settlement remains an aspiration. The return problem. Once you're there, how do you leave? If the infrastructure for leaving is not in place, a colony quickly turns from a bold outpost into a one-way prison. Every person who lands on another world must face the haunting question: how do you ever get back? On Earth, a launch pad has access to vast industries, providing liquid oxygen, refined fuels, tanks and pumps. On Mars or the Moon, none of that exists. To send a rocket home, colonists would need either to bring a fully fueled ascent vehicle with them, an enormous logistical challenge, or somehow manufacture the fuel on site, using unfamiliar resources under harsh conditions. For Mars, some strategies have been proposed, such as using the planet's thin atmosphere of carbon dioxide to produce methane and oxygen through chemical processes. NASA and private companies like SpaceX have studied this carefully, because it offers a potential solution to the return problem. But while the chemistry is straightforward in theory, the machinery to make it happen reliably, at large scales and for years without interruption, is anything but simple. Even if the system works, the sheer energy required to produce enough fuel for a return trip could demand vast solar farms or nuclear reactors, more infrastructure than most initial colonies could hope to build. On the Moon, there is no atmosphere to harvest, but there may be ice hidden in permanently shadowed craters. The difficulty lies in mining ice in locations colder than anywhere on Earth, transporting it safely, and then running complex chemical plants to split it into usable components. Again, this requires heavy machinery, skilled operators, and constant power. Until such systems are proven and tested, the safest approach would be to pre-position return vehicles with fuel already on board. The rocket itself is another hurdle. Getting off Mars or the Moon still requires engines, tanks, and guidance systems. On Earth, rockets can be built in vast, clean rooms, tested on ranges and repaired with fresh parts. On another world, a damaged valve or cracked nozzle could spell disaster with no replacements available. This means any return vehicle must be landed in pristine condition, kept in storage for years if necessary.